Classical computing relies on discrete, pulsing digital binary code. Quantum computing replaces those rigid values with continuously shifting probabilistic geometry. These systems accelerate scientific calculation by applying the laws of superposition, entanglement, and extreme thermodynamics. The absolute baseline of all classical computing architecture is the bit. It exists strictly as a definitive 0 or a definitive 1. For decades, increasing a machine's computing power made cramming more of these binary switches onto a single physical substrate. Even massive, room-sized mainframe networks operate on this exact same linear, discrete logic. We are now approaching the physical and thermal limits of how closely classical transistors can be packed together before electron interference breaks the system. To bypass this physical limit, scientists have moved away from Boolean logic toward systems based on quantum linear algebra. Expanding computational power exponentially requires entering the probabilistic mechanics of quantum states. This equation defines the state of a qubit. Using Dirac notation, we can see exactly how it processes information. Unlike a standard bit, a qubit exists as a linear combination of multiple states simultaneously. The 0 and 1 states are held in tension. The alpha and beta symbols act as probability amplitudes. They dictate the mathematical likelihood of landing in the 0 or 1 state when observed. Translating this into geometry, the qubit state acts as a dynamic vector, moving continuously within a 3D spherical space. This continuous state allows the system to hold all potential probability pathways open at exactly the same time. This potential remains open only until the system is observed. In quantum mechanics, measurement is a destructive act. The physical act of measurement forces the probabilistic vector to permanently collapse into a definitive 1 or 0. Quantum algorithms operate by manipulating these unmeasured vectors to amplify the probability of the correct answer right before that final collapse occurs. Superposition allows a single piece of hardware to navigate vast arrays of probabilities at once, removing classical processing bottlenecks. While a single qubit holds potential, quantum computers rely on the architecture of a multi-qubit system to achieve true scale. This is the mathematical model for quantum entanglement, known as a Bell state. In this precise state, two independent particles become perfectly correlated, sharing a single computational identity. Perturbing one qubit dictates the state of its entangled partner, regardless of physical distance. This instantaneous, non-local correlation originally faced fierce scientific skepticism. Albert Einstein famously rejected the mechanism, characterizing it as spooky action at a distance. Engineers now use this correlation as a functional tool for high-speed computation. Entanglement acts as a computational force multiplier. By linking qubits, processing power scales exponentially with every single qubit added to the array. This highly correlated architecture maps to complex natural systems, allowing researchers to simulate intertwined variables like molecular bonds for targeted medicine. Superposition creates parallel computational paths, while entanglement binds them, enabling the machine to calculate millions of interdependent variables simultaneously. Executing this mathematics in the physical world requires overcoming severe environmental limitations. The primary engineering hurdle preventing widespread quantum computing is a process called decoherence. Qubits are fragile. External kinetic energy, ambient heat, minute vibrations, or stray radiation acts as an accidental measurement, forcing the quantum state to prematurely collapse. You can visualize thermal noise as high-speed kinetic particles bombarding the pristine vectors of the quantum state. This environmental interference forces the superposition to collapse, turning complex probabilistic paths into static classical data. The current physical solution to decoherence is extreme cryogenic isolation within specialized vacuum chambers. Inside these chambers, the operating temperature is driven down to roughly -273 degrees Celsius. This threshold is close to absolute zero, an environment colder than the vacuum of deep space. Reaching absolute zero strips kinetic vibration from the physical environment, effectively freezing thermal noise. With the kinetic energy halted, the environmental interference stops and the quantum vectors restabilize. Maintaining quantum logic is a battle against thermodynamic entropy. Without perfect isolation, the complex mathematics immediately dissolve. These extreme operating conditions mean quantum computers are not a replacement for standard classical desktop CPUs. For deterministic tasks like rendering 3D video, processing text files, or managing basic arithmetic, classical computers remain the superior choice. A quantum computer is a specialized instrument engineered for multivariable, probabilistic simulations. These systems are built for tasks where classical machines fail, such as mapping climate patterns, optimizing AI networks, and accelerating medicine discovery. This raw probabilistic power also introduces a specific threat to digital cybersecurity. Current encryption algorithms work because a classical computer would need thousands of years to try every potential solution sequentially. An entangled quantum system can navigate massive encryption pathways simultaneously, compromising current security protocols. In response, tech firms and governments are now developing post-quantum cryptography algorithms. To protect our sensitive data, these new methods use complex, multidimensional lattice-based structures that a quantum state cannot easily map. Successfully operating these machines requires a precise marriage of probabilistic mathematics and cryogenic engineering.